Great. So yeah, thank you very much for the invitation today. I'll be discussing a little bit our journey when creating a large-scale data set of X-ray segmentation masks, which were automatically generated by us, and how the fairness topic crossed this creation of the data set, and how we managed to incorporate at least some estimates of how fair these segmentations are. So this is work done with my team in Argentina. Where people highlighted here in bold are the responsibles of this work, actually. And the data set I'll be presenting, it's called CheXMask. We released this a couple of months ago. It's still under, the paper itself is still under review, but well, since we were invited to discuss this, I thought it was a nice opportunity to put there a little bit of the challenges that we faced when creating this data set. So just a little description of the data set itself. We are talking about a derived data set, basically. So it's about, oh, sorry, I just, there it is. It's like a derivative data set in the sense that we do not create the images. We did not obtain the images. We took several data sets publicly available, and we augmented this data set with segmentation masks, because we believe these are important and useful for different downstream tasks when you analyze X-ray images. So the dataset contains segmentation masks for heart and lungs for about 600,000 images. Interestingly, we also produced landmark correspondences in this segmentation, so you can actually track different parts of the organ across the whole population. This is especially useful if you are doing some kind of shape analysis on these organs. But more importantly to this talk is that we tried to create an automatic quality control metric per subject, because here we are producing the segmentations, right? So we want to tell the people how trustable somehow they are. And in this talk, I'll be discussing a little bit about how we, what techniques we leverage to create these metrics. Also, a little bit, I'll be discussing on how we incorporated expert humans and the way they interacted with this creation process. And finally, and I think more relevant to this seminar, is how could we assess fairness, or at least we try to assess fairness in this new data set, considering these new segmentation masks, to detect potential demographic groups where the model may be failing, and also incorporate this information when releasing our data set. So a little bit of this journey. So we started with data preparation, basically. So I'll discuss the three parts, basically, data preparation, data processing, and technical validation. So when it comes to data preparation, first thing we had to do was to basically look out there which chest X-ray datasets were available. We took the 6 biggest datasets. Actually, many of them have been already discussed in the previous talks. And basically, we filtered the images, because we will be focusing only on frontal images, okay? So we apply some inclusion criteria, basically selecting only the front images and discarding lateral images, for which we are not going to be producing segmentations. Then, when we were preparing the data set, of course, many different type of challenges appeared. Image standardization, for example, was one of them, where we had to, of course, resize the images, but also apply some kind of intensity normalizations. Then we also looked at the metadata of these data sets, and we tried to somehow say, okay, this is the type of metadata that is available for all of them. We have gender information, sex information, gender information, and kind of harmonize a little bit that. And also, and really important, I believe, analyze if the terms of use of every data set were allowing us to use these data sets for creating this kind of augmented version of the data set or not. And with that, then, we basically had this huge database of 600,000 images that we started processing. And during the last years, we have worked a lot on creating segmentation tools for X-ray. And this is, I mean, I'm not going to go here in the talk on the details of the segmentation method, but just to have a brief idea of what the method does, it basically takes the X-ray images, and instead of producing pixel-level segmentation masks, what we developed is a method called hybrid GNet that produces graph-based segmentations. So we are producing graphs that represent the contour of the different organs, okay? And we observed, actually, that this model that we proposed is much more robust to artifacts, which are one of the main challenges that we had to overcome during the creation of this data set, how to deal with artifacts. For example, here I'm showing you some peacemakers here, but there are other type of artifacts that can appear. And if you look at what standard pixel level segmentation methods do, usually the problem is that they are going to be failing when segmenting images with these kind of structures. Our method, which is based on graph segmentations, it uses graph generative models to generate this segmentation, ensures anatomical plausibility, what we call anatomical plausibility. And it's basically the fact that the segmentations that we are producing live in an anatomically plausible space. And this is something that was nice. I mean, if you are interested on this part of the discussion, you can actually check our paper that discuss exactly that part of the method, how to create anatomically plausible segmentations. But this is not the focus of this talk. In this talk, I want to actually focus on a different challenge that we faced when creating this data set. That was, okay, I mean, when we were discussing the creation, especially with the doctors, we said, okay, we are going to release a data set with segmentation masks, and people are going to start maybe using that. We want to tell people how good these segmentation masks are, but we are talking about 600,000 images here. So we cannot ask actually doctors to analyze every one of these segmentations. So the solution we found, and I'll be discussing it a little bit now, was to combine human expertise with automated methods to produce some metrics that are good surrogates for quality metrics in the domain of image segmentation. So I will explain here the three different type of validation techniques that we use when creating these data sets. Of course, one of them was simply asking expert physicians from Hospital Italiano de Buenos Aires, who are actually is actually one of the biggest hospitals in Argentina, with whom we are collaborating on this project. So we asked them to segment manually, to correct actually segmentations that we produce for 30 images sample from every one of these sub datasets, I would say, from CheXpert, from the NIH dataset, for all the different datasets that we employ. And so with that, we had some kind of ground truth, expert ground truth, but of course, it was just a subset of the images that we could evaluate with that. And using that, we produced the first estimation of the quality of our segmentation masks. For that, we use two standard metrics, dice coefficient and Hausdorff distance. These are two standard metrics that people use in the community of medical imaging, especially to measure the quality of the segmentations. Dice is about measuring overlapping between the segmentations, and Hausdorff distance is the maximum distance between the contours of what you have produced and the ground truth. And so if we start with that, we can see that actually for this subset of the images where we had the capacity of computing these metrics, the performance of the method was pretty good for all of them. So this told us, okay, in general, the method seems to be doing pretty well on these new data sets, on these unseen data sets. But then we wanted to have an individual estimate. We wanted to say, hey, for every one of the segmentation masks, we want to produce a dice, an estimation of the dice coefficient and an estimation of the Hausdorff distance. And for that, we leveraged something that was proposed a few years ago by Ben Glocker and his team that is called reverse classification accuracy. So reverse classification accuracy is a method that allows you to get a surrogate and estimate of the dice coefficient without any ground truth annotation. And let me briefly explain you how this works. So the idea is that I will have an image, I, for which I produce a segmentation. And I will also have a segmentation mask that is basically the prediction of my model. This is the one I will try to see what is the quality of that segmentation. Then, so the idea is that I will have a database of images that were already segmented, images for which I had ground truth annotations, a small database. And what I will do is to take the original image, the image I'm trying to audit now to see what's the quality of the segmentation, and register this image to every one of the images in my dataset. So I will register it in an affine plus non-rigid deformable way. So I will take this image and deform it so that it matches every one of the other images. I will take the resulting deformation field, and I will apply this deformation field to the predicted segmentations that I have. And I will also deform these segmentations. And what I will measure now is the dice coefficient or the Hausdorff distance or wherever metric I want to estimate with respect, between the predicted segmentation that was deformed and the ones corresponding to my training database somehow. And what's the intuition behind that? The intuition is that if the segmentation was good, if the model produced a good segmentation, then this segmentation should be good enough to segment some of the other images that I had in my dataset. If the segmentation was bad, it's not going to be able to segment any of them in a good way. So the idea is that after transferring these labels to my training database, I compute some metric like dice or Hausdorff, and then I pull a number out of all of them by doing a mean or a max. And what you can observe is that actually by estimating the dice coefficient using this method, you get a really good correlation between the true dice coefficient here in the y-axis and the predicted, the estimated dice coefficient in the x-axis here, estimated using this reverse classification accuracy estimator that I was telling you. Actually, considering max or mean seems to be more or less the same. Here we continued using the mean operation for pulling a number here. And what we did, it was to create this histogram of dice, estimated dices for all the images in our data set, for the 600,000 images. And we observed the distribution like this one. And then we basically analyzed a little bit, okay, what's the RCA estimated dice coefficient per sub dataset. So in that way, we could see that actually, if you, for example, take images for which the estimated dice was too bad, was really low, what you observe is that these images are completely out of distribution images. For example, in the candid dataset, we observed that these images, oops, sorry, my screen changed. There we go again. Okay. For these images, we observed that they were out of distribution images. For example, images that produce a really low dice coefficient, we were able to detect lateral images that were mislabeled, or even an image of a cell phone that was part of this data set, or really partial views, which you were not able to segment. Okay, so in this case, the model acted as an out of distribution detector somehow. And finally, as an extra technique that we apply here to validate the quality of the estimated segmentations, we took this approach of retraining a new segmentation model using the segmentations we produced. Okay, so we produced a bunch of segmentations. Now we train a new segmentation model, and we test this model, the whole model, in the images that we had in our training set, like apart, images for which we have ground truth. And so this is another new estimator, because what it means is if the segmentations are good, then they should be good enough to train a model that can segment other images. And so when you measure actually the quality of a model that was trained with the segmentations that we produced, and tested on different segmentations for which we have ground truth, we observed that the dice coefficients and Hausdorff distances were really good, actually comparable to what you would get if you train with images with real ground truth, with manual expert annotations. So these three different ways of computing some kind of metric for the quality of the segmentations without any ground truth were really useful for us in creating this quality estimation index, that we are also releasing together with the data. That was one part of the technical validation, but then we said, okay, is there any way in which we can also look at the fairness of, can we use this metric basically to look at how fair these segmentations are in an unseen population? We started, I started working on fairness many years ago. Actually, we got this paper published in PNAS that I'm not gonna describe a lot now. It's just simply to mention what was already mentioned in this discussion here, that models, segmentation, classification, detection, every model that works on medical images can be biased due to different type of spurious correlations or different reasons that we can find. So we have published a few articles actually on this domain, and not only us, many people have noted that in different contexts, right? In particular, there was this really interesting paper by Esther Pujol and Andrew King and people at King's College that showed that segmentation models can be biased. This is what we showed, but basically I'm more interested on this part here. They showed that the segmentation models can also be biased in the sense that, for example, if you are segmenting heart structures in MR images, you can have really different dice coefficients for white people, for example, or people of different ethnicities. Like there are strong differences here, mostly due in this case to an underrepresentation of these ethnicities. So we say, okay, this problem can be there. So is it possible to audit? We had also observed that in this setting of lung segmentations for age. So we observed some age biases here. And so the point is, if I want to really audit for fairness one of these models, what I have to do is to take my trained segmentation model and evaluate it on the different subgroups that I will consider, right? This is usually the way we audit these models. And then we compute some fairness metric that in case of segmentation is usually the gap between the dice coefficient for one population and the other. Now, the problem is, and one of the main limitations, that we require ground truth annotations to compute this metric. So how can we do this estimation without requiring ground truth annotations? Because here in our big CheXMask dataset, we don't have ground truth. And actually, something that also motivated this our work on auditing fairness in unseen data was this work actually published by Jessica and her team, where they show that fairness does not always transfer across distribution shifts. So here, for example, there is a case in which a model in a certain source domain was fair, kind of fair across distribution, across different age. But then when you go to a different target domain, the model is not fair anymore because there was some change in the distribution. So even if we audit for fairness on our segmentation model for our source data set, then when we go to all these other new data sets, the model may be unfair. And so we came out with this idea of doing what we call unsupervised bias discovery in deep segmentation networks to anticipate biases. This was published this year in one of the MICAI workshops on fairness. And what we did, it was to simply show that the estimated dice using reverse classification accuracy can be used as a proxy, the gap between these two things. I'm not going to go into the details now because of time, because I'm already reaching the 20 minutes. But we show that basically with different experiments, the correlation between what the gap in dice for two different subpopulations, let's say, for example, men versus women, like based on gender or sex, and the estimated gap using our reverse classification accuracy is a really good estimator of fairness in scenarios where we don't have ground truth annotations. And we apply this technique to this CheXMask data set that we have. And this is the distribution of estimated dice coefficients for different subpopulations. And something, for example, that was really interesting to us was this big difference in the distribution. You see here in blue, you see the, in blue, you see the posterior anterior images. And in orange, you see the anterior posterior images. And you can see that most of the anterior posterior images tend to have a lower dice coefficient than images from the posterior anterior. This is the estimated dice, okay? We don't have ground truth for that. This is the estimated one. But when we show these to the radiologists, they say, yes, this makes completely sense, because actually the anterior posterior images tend to come from hospitalized patients who are more difficult to position in a standard view, and sometimes they have also a different type of artifacts because they are hospitalized. And so it makes sense that the model is failing more there. But the nice thing is that we were able to show that using this estimated metric. For other type of things, like for example, for gender, we didn't find a big bias. So it seems that the model is not biased with respect to gender here. However, for age, we found that certain ages had much lower dice coefficient, especially the pediatric patients. So this is it for my talk. I basically wanted to tell you a little bit about the story. Here you have the paper that is still under review, and you can access the dataset as well. And there are things we want to do to improve that even more. Like, for example, the work that Amelia has been doing on augmenting these chest X-ray datasets with non-expert annotations related to artifacts is something that we really want to push also on the CheXMask dataset, but also expanding it to other type of anatomical segmentation and additional structures. So there are challenges when you want to create a new dataset like this one. We believe it's important, and whenever possible, it's nice to provide this kind of automatic quality assurance metrics, like the estimated RCA. And they can even work as surrogates to audit for fairness in situations where we don't have ground truth. So I believe this is really encouraging and something that we can explore more. And of course, the metric I showed here is especially tailored for anatomical segmentation. You cannot not use RCA in other scenarios, but you may come up with other metrics for classification or detection, for example, leveraging uncertainty as a metric for that in case of classification that could be of interest. So I want to thank all the organizations that supported this work. And yeah, with that, I conclude. Thank you very much.